Welcome to week 2 of our C++ track. This week, we're going to be talking about how we can create our own types of objects. As a reminder, an object is a concept in programming that groups related data and behavior. Classes are how we define the types for our objects. A class describes all of the member variables and functions for a type of object. Let's take a look at what this looks like in code. We declare a new class with the class keyword, then the name of our new class, a set of curly braces to hold our class's body, and finally a semicolon to close out the declaration. With this new person class declared, we can create an object of type person. This is an empty object right now because we haven't given it any members. Let's fix that by giving our person a name and an age. We add a member variable to classes simply by declaring them in the class body. We can declare a string variable for the name and an int variable for the age. Now every person instance will have its own name and age. Like any other object, we can access members with the dot operator. But if we try to print out the name of our person, we get an error telling us it's private. When a class member is private, it can only be accessed by member functions of that class. Since our main function is not part of the person class, it can't access the name member. To make a member accessible by other code, we need to mark it as public. We do this with something called an access specifier. And that looks like this. We use the keyword for the type of access we want to grant and follow it with a colon. Everything after this line is now public. You can have as many access specifiers in your class as you want, but most of the time we just use one for each access level. So we might have a section of public members and then a section for all of our private members after that. Now that name is public, our code compiles and prints out an empty line. It's empty because we haven't set the name to anything else. One way to set the name is by giving our members default values. We can do this by adding an initializer to our member declarations. Now every person instance starts with a default name of Jane Doe and a default age of 0. Of course, we don't really want every person object to have the same name and age, so how do we initialize P with a specific name? Well, one way is to use Aggregate Initialization. We add some curly braces after our instance name, and inside of those braces, we give values for all the members of our class. Here we've given P the name Benjamin and the age 42. This works for any classes that don't define their own constructors, which is great for simple classes that don't need to be set up in a specific way. For classes that do need to do something more interesting as they're being set up, we use constructors. Constructors are special functions that get called when our object is initialized. To declare a constructor, we write a member function with the same name as the class and no return value. To make this constructor initialize our two member variables, we'll add two parameters, nameVal and ageVal. Then we forward the values on to our actual member variables using the member initializer list. This is a series of initialization statements that goes between the constructor's signature and body and starts with a colon. Here, we're just copying the values from our parameters into the actual class members. If we needed to do anything fancier to set up our object, like open a file or a network connection, we could do that in the constructor body. Note that when calling a constructor, we can use either curly braces or parentheses. Both of these call our person constructor just the same. The counterparts to constructors are destructors. Destructors are special functions that give our object a chance to do any cleanup or finalization it needs to do before it stops existing. We can add a destructor to our class by adding another special function whose name starts with the tilde character. Destructors can't have any parameters because we don't explicitly call them in our code. The destructor for an object is called automatically when the variable holding that object goes out of scope. We can see this in action by printing out a message in our destructor. Our message is printed as we return from the main function. Let's make our demo class a little more interesting with a few more changes. We want to control the ways other parts of our code interact with our member variables, so we'll make them private. Our line printing out the name won't compile anymore, but that's fine. We'll add a new member function named introduceSelf that will print out a short introduction for the person represented by the object. And we'll add a second function named celebrateBirthday that increments our person's age. Note this const at the end of the signature for introduceSelf. This tells us that this function can't change any of the members in this object. It is safe to call this function on a constant person object. Because celebrateBirthday doesn't have this const keyword, it is allowed to modify the object. We can't call celebrateBirthday on a constant person object though. If we try it, we get an error message that says passing const person as this argument discards qualifiers. The qualifier it's talking about is const, and the this it's referring to is the object we're calling the function on. This in C++ is a keyword that names a special pointer. I know we haven't covered pointers yet, but we don't really need to talk about this. Whenever we're writing code inside of a member function, this just gives us a handle to the specific instance of the object we're working with when the function gets called. We could rewrite our functions using the this pointer to access every member. None of the behavior has changed here, but it shows that this really does just point to our current object. Most people don't write code like this, but the this pointer will show up in other contexts, like the error message we saw a moment ago. So far, we've been writing everything in one file. In practice, classes are usually split into their own header and implementation files. Compiler Explorer doesn't give us multiple files, but we can talk through what that separation would usually look like. Here I've blocked off 3 sections in our code. The first shows us what the header file, person.hpp, would hold. The second shows us the contents of person.cpp, our class's implementation file, and the third section shows us our main file, main.cpp. Header files for classes usually contain the class declaration, but not the member function definitions. We get the signatures for all of the functions, but not their bodies. We can see what functions this class offers, including all the details about parameters and return types. We even get qualifiers, like the const on introduce self. Anyone who wants to use our class just needs to include this header, like we would down here in main.cpp. The function bodies have all been moved into person.cpp, our implementation file. This file starts by including the header so we don't have to repeat all the declarations. The rest of this file gives us the definitions of our member functions. Notice that each function name is prefixed by the name of our class and a double colon. This is what clues our compiler into the fact that these are definitions of functions from a class and not just totally new functions on their own. Most classes you'll see will be split up like this because it makes it easy to use the class in other code. There's one more thing for us to talk about in this video. The struct keyword. In C++, struct means almost exactly the same thing as class. In our examples, we could have replaced class with struct and nothing at all would change. Both keywords tell the compiler that we're defining a new object type. The only difference is their default access specifier. In a class, the default access level is private, like we saw towards the start of this video. In a struct, the default access level is public. And that's it. That really is the only difference. At least, technically. In practice, developers have come up with different conventions for what it means to use class versus struct. Structs are conventionally used for objects that just bundle data together with no extra invariance or rules about the values. Classes often get used for objects that keep most of their data private or expose most of their functionality through functions. Again, these are just patterns, not strict rules imposed by the language. These conventions let us more clearly communicate our intentions to other developers. That's all we want to cover about creating basic classes. We'll be covering more things you can do with classes in future videos.